Begin recording 2. This is Dr. Benson again, PhD in Aerospace Engineering, on behalf of Mecha Industries. This second audit is a continuation of the new request for proposal that will last from February to October in the decade and year of 24 for original Mech designs. This entry is for the CupCup contract. Entry name WASP, or Weaponized Aerial Solo Patrol. Requirements and how to enter are linked in the description of this audit. As explained in Part 1, the initial frame of the WASP is complete and ready for implementing system functions. The first item the team implemented was the forward machine guns. As the build becomes more complex, we have to rely on more diverse methods, so microplasma cutting was utilized. The steel barrel is hardened, so a diamond grinder was used at low speed to minimize heat creep and risk of injury. The machinist has been reprimanded for drinking too much caffeine before precision work. Unless otherwise specified, cyanoacrylate contact welding will be used for all attachments in this audit. The WASP is a lightweight reconnaissance vehicle. The twin machine guns are not enough to take down a battle mech if encountered in the field, but they will hopefully prove useful in other scenarios. With the machine guns attached, we can continue adding functionality to the legs and know that we are not blocking the muzzles. Reinforcing the feet provides a strong mount for attaching a hydraulic piston. Careful measurements and machining allow us to make precision parts with flush seams that can handle the high hydraulic pressure while taking the load of the mech. Note, because there are 6 legs, even with a piston failure, there will be enough support for the entire mech. The non-functional end of the piston is simply mounted within the reinforced foot, while the active half is mounted to a pivoting inlet. Individual hydraulic pumps are attached to each leg, rather than having one oversized pump mounted to the body. The redundancy is planned to prevent failure of all legs in case a central pump is damaged during use. Air-grade aluminum was used for the hydraulic tubing due to its lightweight, ease of installation, and tendency to split under failure rather than explode shrapnel. Each leg needs the piston and pump to be meticulously connected and tested. Any leaking connections will essentially leave the leg useless. After sealing the piston housing, caps were placed over the knee joint connections in order to prevent dirt and grime from wearing down the pivot. With all 6 legs completed, we could move on to the electrical work. Junctions were attached at every hip joint, with a centralized array for connecting with the rest of the WASP's computer systems. Gaps between electrical components were filled with powderized talc in order to prevent vibrations and shifting of landing gear components. The electrical work was implemented with lead-free components. Lead is obviously denser than other metals, and we needed to keep the mech as light as possible for flight efficiency. Although we could have implemented a 3-phase cycloidal drive, the extra hassle of installing a specialized driver board was not seen as beneficial in this use case. After internal discussion over the efficacy of the forward machine guns, it was agreed upon that additional rockets could be installed without going over budget and overweight on the mech. There is not enough room to install rocket pods that are already available on the market, so we made custom launchers that are as compact as possible. As with the machine guns, these rockets will not be enough to take down a full-size combat mech, and it is recommended to evade instead. These rockets will be more useful against other scouting and light vehicles. There are a total of 4 rockets available per flight. There is no collision with the legs when landed, but the forward legs need to be lowered for clear line of sight. A lot of technical work needed to be done on the primary turbine engine. The nozzle flap hinges were the first parts to be installed. Aluminum guide rails were straightened between 2 granite surface plates. These rails are necessary mounts for attaching the fuel monitoring systems, which have flat bases and cannot attach to the cylindrical engine body. The round turbine can cause difficulty with marking perpendicular lines, but utilizing magnetic clamps with various machinist tools can ease some of the headache. An additional fuel flow controller was installed, which can be used as an emergency shutoff for the engine. The emergency shutoff valve has an extra remote circuit in case the flight computer loses a hardwired connection to the turbine engine or fuel pumps during use. Flanges were installed for fuel intake behind each nozzle flap. Power junctions were made from old electrical boxes and installed with extra metal bracing. Microplasma cutting was used to start the fuel inlets, which could then be machined with appropriate boring tools. Gasket seals were attached to each inlet in preparation for the fuel lines themselves. Although the fuel is under pressure, the forces involved are not the same as the leg hydraulics. Therefore, tin-based fuel pipes were used for ease of installation on the complex curves of the turbine housing. Aluminum is easy to manipulate, but even so it would add unnecessary difficulty in finalizing the fuel line installations. Every component on the Mech is dry fitted before welding in order to guarantee the highest quality possible. With the fuel lines connected, each nozzle flap fuel sensor is individually wired to the power junctions installed earlier. Electrical work is tedious, but we must remain vigilant during implementation. Any wrongly wired cable can lead to devastating issues when the primary engine is turned on for the first time. Mounting brackets have to be utilized to prevent the wires from jostling loose during flight. This will also help keep the cables organized for maintenance and testing purposes. With the engine almost ready for testing, a manual lever is attached to the emergency shutoff. One last diagnostic board makes for a finished system. The vertical microengines are not nearly as complex, but still need the appropriate system connections in order to function. The previously installed wing gussets were no longer needed and proved problematic for attaching additional bracing and functionality to the air intakes. Maintenance hatches and fueling ports were the only other major components needed on the wings. The rear tail wings do not have any additional engines or functional components to worry about, but because of the long spine of the Mech and potential for flight issues from the oversized primary engine, additional sensors have been added for flight computer data and stabilization. Miscommunication led to a large gap being left in the body, although we stated in the first audit that the cockpit would be pressurized. We also intended the air intakes to feed the primary turbine blades, but it is better to slipstream the air back towards the rear wings. Occasionally, chamfering panels will help them sit flush in corners where weld beads are in the way and difficult to remove. Finalizing system hookups on the back of the cockpit took some effort, but we were able to save on precious materials by reusing some readily available wires sitting in storage. The tail has 2 additional cooling vents to manage the radiant heat coming from the primary engine. With most system functions connected, the internal spindle for the primary engine was finally ready for installation. Spare parts were used to mock up and measure necessary components. The bulk of the fuel outlet was made from a repurposed pump housing, but the spindle needed to have precise dimensions and was made from stock pieces of aero-grade aluminum. This engine is a hybrid aerospike design, and with the internals finished, the final touch of the WASP stinger was finally put in place. To ensure minimal problems from vibrations, the fuel pipes were fixed to the engine housing. While the rest of the Mech was quality assurance tested by Mecha Industries experts, the cockpit windows could finally be worked on. The complex curves of aerial vehicles leads to tricky window framing, so special polymerized material was utilized to create a seamless front hatch. The frame was hardened using our new portable UV kiln. Only authorized employees with proper UV eye protection are allowed to use the new device, and individuals with exposed skin have been reprimanded. A final pass was made across the entire Mech, with rivets to support pre-existing welds across all components. Unlike land mechs, this lighter aerial machine requires less rivets to minimize weight and impacts to aerodynamic drag. In our upcoming 3rd and final audit, the WASP will receive a protective paint job, and the final specifications and test results will be revealed. Attached to this audit is a submission of completed work. Valuable patron contributions have been recognized. And recording too.